Morning all. Today we are going to discuss about Nyquist Stability Criterion in control systems. Okay, last class we have discussed about polar plot, how to find the stability by using polar plot, how to construct polar plot with numerous examples. Nyquist Stability Criterion, it is a graphical technique used in control engineering for determining stability of a dynamical system. The stability test for time-invariant linear systems can also be derived in the frequency domain. Basically, it is depending upon the complex analysis, the result known as Cauchy's principle of argument. The given system, you can say here, the system transfer function is a complex function. By applying Cauchy's principle of argument to the open loop system transfer function, we will get information about the stability of closed loop transfer function and arrive at the Nyquist stability criteria. Before going to discuss about Nyquist stability criterion, we need to know few points before finding the stability of system by using Nyquist stability criteria. So in this case, we should know about first what do you mean by principle of argument, what is a mapping theorem, encirclement, and Nyquist contour or Nyquist path, and also Nyquist plot. So these points you should know. Okay, first what do you mean by Nyquist stability criteria? Okay, now the closed loop transfer function C of s by R of s, that is equal to G by 1 plus G into H. So from this you can take characteristic equation. So the characteristic equation of the system is 1 plus G of s into H of s equal to 0. Let us take that is the left hand side polynomial. You can say 1 plus G of s into H of s equal to f of s, because it is another in terms of s domain only. So you assume that is n is a number of anti-clockwise encirclements. Mathematically, n is equal to p minus z, where p is a number of poles of f of s or poles of the loop transfer function lying in right half of the s plane. Z is a number of zeros of f of s. Okay, the stability is related to the poles lying in right half of the s plane. And so, while applying principle of argument, only poles and zeros lying on right half of the s plane are considered. Or in different way also you can take. So the principle of argument can also be used to find the number of poles of the closed loop transfer function lying on right half of the s plane. Here if we take m is a number of encirclement, so this is the clockwise encirclement. Previously you have taken n is the anti-clockwise and this one it is a clockwise encirclements. Mathematically that m is equal to z minus p, where p equal to 0. Suppose if it is a number of poles right half of the s plane is 0, then m equal to z. So there is no right half of the open loop poles. Number of clockwise encirclements gives the number of poles, okay, lying in right half of the s plane. Nyquist stability criterion can be stated as follows. If the G of s into H of s contour in the GH plane corresponding to Nyquist contour in the S plane encircles the point minus 1 plus J0 in the right anti-clockwise direction or counterclockwise direction as many times as the number of right half of the S-plane poles of G of S into H of S. Then the closed loop system is stable. Okay, this is the statement of the Nyquist stability criterion. By taking this, you can examine the stability of the linear control system by using Nyquist stability criterion. So, we come across the following three situations. No encirclement of -1 plus j0 point. This implies that system is stable if there are no poles of G of S into H of S in the right half of the S-plane. If there are poles on right half of the S-plane, then system is unstable. That is the first situation. Coming to second situation, that is an anti-clockwise encirclement of -1 plus j0 point. In this case, the system is stable if the number of anti-clockwise encirclements is same as number of poles of G of S into H of S in the right half of the S-plane. If the number of anti-clockwise encirclement is not equal to number of poles on right half of the S-plane, that is n is not equal to p, then system is unstable. That is second condition. And third condition is, that is reverse, clockwise encirclement of -1 plus j0 point. In this case, system is always unstable. Okay. Now, already we have discussed about what points to know before the construction of Nyquist plot and also finding the Nyquist stability. So, this is the one point, Nyquist contour, or sometimes you can say Nyquist plot. Okay, these are the Nyquist contours. Based on the transfer function, we have to select Nyquist contour before mapping the sections. That means if you are taking first figure, this one Nyquist contour, when there is no pole on imaginary axis. Simply saying here, on this axis there is no pole in the given transfer function. If any pole at origin or number of poles at origin, then you have to take Nyquist contour, that is second one. For example, if you are taking, so 10 by S into S plus 1 into S plus 2, that means S is there at origin. Okay. Similarly, if the transfer function is having number of poles on origin and also on the imaginary axis at that time, you have to take Nyquist contour this way. Similarly, how number of, that is depending upon the poles, if multiple poles on imaginary axis and also at the 0, so then you have to take this fourth Nyquist contour. Okay, so these are the Nyquist contour. How it works, just I will explain in the next step. So if you are taking first one, that is in this there is no pole at origin or on the imaginary axis. Okay, so here we have three sections, C1, C2 and C3 sections. Here C1 section, it is on the imaginary axis. Frequency varies from 0 to plus infinity. Okay, and this one it is very good. And second section, it is on S-plane. You can take here, it starts at, that is an angle is varying from plus pi by 2 to minus pi by 2. Here the radius, it is having infinite amplitude. So that's why here you need to assume that is a S equal to limit r tends to infinity r into e power jt. Theta is varying plus pi by 2 to minus pi. And third section it is C3. Here again frequency is varying from minus infinity to 0. Okay. So using the loop transfer function G of S into H of S, the Nyquist contour C of S plane is mapped to GH, that is G of S into H H of S plane. The mapped contour in G of S into H of S plane is called Nyquist. Say we can say here G of S into H of S contour. Okay. Now another point is principle of augment, because Nyquist stability criterion is on the principle of augment only. If let's say P poles and zeros, Z zeros of F of S, or it is a Q of S or F of S, are confined by the S plane contour, then Q of S plane contour must enclose the origin Z times in the clockwise direction, then and P times in the anti-clockwise direction. So generally, number of poles should be greater than number of zeros. This relation between enclosure of poles and zeros by the S-plane contour and enclosed path in the complex pole is known as a contour. And the encirclement of origin by the F of S plane contour or Q of S plane contour is known as principle of augment. And next point is encirclement, because this is the main important for finding the stability. Any specific point is declared to be encircled by a closed path if it lies inside the closed path. Okay, if suppose that closed path, so if any point it is inside that -1 to j0 point, at that time only, based on that only, you can take number of encirclements, whether it is a clockwise direction or anti-clockwise direction. Another one, it is a mapping theorem. For any closed loop system to be stable, the Nyquist plot of G of S into H of S should encircle the point -1 plus j0 as many times as the number of poles of G of S into H of S that are in the right half of the S plane. Mathematically, we can express this one. Number of encirclements is given as n equal to P minus Z, where n is the number of encirclements of the point -1 plus j0 and P is the number of poles that are in the right half of the S plane, and zeros is number of zeros. And for a stability of closed loop, Z should be 0. That means n is equal to P. N equal to, okay. So in the next class, we'll discuss about Nyquist plot and how to construct or how to sketch the Nyquist plot. Thereafter, we will take some examples of the Nyquist plot. Okay.